A linear loaded dipole is a type of shortened antenna where a portion of the radiating element is folded back on itself to create a shortened transmission line stub. This fold adds the necessary inductive reactance to electrically lengthen the antenna without requiring the massive physical footprint of a full-size half-wave dipole. If you are trying to make an existing 80-meter dipole resonate on the 160-meter band without increasing its total physical length or shifting the feed point, linear loading is arguably the most efficient way to achieve it. When you fold the wire back parallel to the main element, the parallel section acts like a shortened transmission line stub rather than a pure radiator. This stub introduces inductance to the antenna system. Unlike a traditional loading coil, which concentrates the inductance in one localized spot, linear loading distributes this inductance along a section of the antenna. For homebrewing antennas, especially when running external power like linear amplifier, linear loading offers distinct advantages over traditional base or center loading coils. Efficiency Q factor high for linear loading, lower resistive losses because the inductance is created by continuous thick antenna wire. For coil that is inductive loading, it is lower. Coils introduce resistive losses which turn your RF output into heat. Bandwidth broader for linear loading, maintains a slightly wider usable SWR curve across the band. Narrow for coil loading. High Q coils create a sharp resonance, often requiring a tuner for small frequency shifts. Power handling is excellent for linear loading, handled entirely by the wire gauge, no risk of arcing between tight coil windings. Power handling is limited for coils. Coils can overheat, melt or arc if not heavily built for the amplifier's output. Construction is mechanically complex for linear loading, requires a rigid spreaders like PVC conduit to keep the wires parallel and evenly spaced in the wind. While for coil it is mechanically simple, just insert a wound inductor in line with the wire. To build or modify one, the parallel wires must be kept perfectly separated to function correctly. Spreaders use lightweight, non-conductive material like CPVC pipes, fiberglass rods or even electric fence insulators. Drill holes to route the wire through. Spacing. The exact spacing between the parallel wires isn't hypercritical for resonance, but consistency is vital. A gap of 2 to 4 inches is standard for HF bands. Wire routing. The wire goes out from the feed point, passes through the spreaders, turns back at a specific length, routes backward towards the center, and then turns again to extend outward for the rest of the antenna leg. The ladder line hack. Instead of dealing with individual wires and custom spreaders, many builders use a length of 300 ohm or 450 ohm twin lead or ladder line for the folded section, shorting the ends as required to create the stub. Calculating the exact wire lengths for a linear loaded dipole is more complex than a standard dipole because the folded parallel wires act as a shorter transmission line, introducing distributed inductance. If your goal is to build this 160-meter antenna without increasing the total physical span beyond the footprint of a standard 80-meter dipole, that is approximately 130 feet total or 65 feet per leg, you will need to rely on a 3-wire fold to achieve resonance within that restricted space. Here is how to calculate the dimensions. First, calculate the full size of a standard half-wave dipole for your target frequency. Example 1.85 MHz. Please note that VU 160 meter band is only up to 1.825 MHz. A common formula for length of a dipole in feet is 468 divided by the frequency in megahertz. So that will come to around 253 feet. This means a full-size 160 meter dipole requires roughly 126.5 feet of physical space per leg. By keeping the antenna confined to roughly 65 feet per leg, you are physically missing about 61.5 feet of wire reach on each side. You cannot simply fold 61.5 feet of wire back into the available space to make up the difference. When you fold the wire back parallel to itself, it forms a shortened transmission line stub. This generates distributed inductive reactance XL, which electrically lengthens the antenna. The inductive reactance provided by a shorted stub of length L is calculated as XL is equal to Z0 tan of 2 pi L by lambda, where Z0 is the characteristic impedance of the parallel wires determined by wire thickness and the spacing of your spreaders. L is the physical length of the folded section. Lambda is the wavelength. Because this shortened stub acts as an inductor, the actual length of wire needed in the folded section is slightly less than the straight mathematical missing length. Because calculating exact distributed capacitance and Z0 in an open air wire array is highly complex and sensitive to environmental factors, it is best to use established reduction ratios. The linear loading method effectively folds the dipole elements back on themselves. Two-wire fold. With a two-wire loaded dipole, the resonant frequency is reduced to about 0.67 to 0.70 of a standard dipole of the exact same physical length. This would reduce a 160 meter antenna to a physical footprint of roughly 85 feet per leg, which is still too long to fit an 80 meter dipole footprint. Three-wire fold. With a three-wire loaded dipole, the resonant frequency is reduced to about 0.55 to 0.60 of the reference dipole of the same length. A reduction to 55% brings the physical length reach of our 160 meter dipole down to roughly 69 feet per leg, which closely matches your spatial limit. To achieve resonance within a 65-foot physical leg, use the following starting measurements. Total wire, start with approximately 105 feet of continuous wire per leg. The first run the wire from the center feed point outward for 25 feet. The fold the wire back towards the feed point for 20 feet, threading it through non-conductive spreaders to maintain a consistent 2 to 4 inch spacing. The extension. Fold the wire outward one final time and run the remaining 60 feet out to your end insulator. The geometry check. This puts your final end insulator exactly 65 feet from the feed point, that is 25 feet out minus 20 feet back plus 60 feet extension is equal to 65 feet physical reach. Factors like proximity to ground and other nearby objects have significant impact on the actual tuned length, so you should always make the prototype antenna slightly longer than calculated. Leave an extra 2 to 3 feet of wire at the far end of the extension, folding it back on itself so you can trim the antenna while measuring its performance with an analyzer to find perfect resonance.